Okay, hi, I'm Ms. Wong. I realized that determining transformations was a bit hard to understand. Maybe I explained it too quickly. So I'm just going to recap the most important parts. So first of all, the order of describing. So recall that when we translate left and right, we're talking about x. When we translate up and down, we're talking about y. So we put the value next to the according letter. Moving left and right, we're adding plus or minus to the x. Moving up and down, we're adding plus or minus to the y. With reflection and dilation, it felt like we did the opposite thing. So when we reflect along the x-axis, so if this is the x-axis, we reflect along the x-axis or in the x-axis, then we're putting a negative in front of the y. If we reflect along the y-axis, so this is now the y-axis, then we put the negative in front of the x. Same thing with dilation. Now the next thing that I needed to point out before we continue with the video is the order of the description. So in short, I recommend always ordering it as dilation, reflection, and translation. So if you keep the translation later when you're describing things, then you get to the same graph. But the orders can be jumbled up if you're talking about the same direction. What do I mean? Okay, so I'm going to do two things at a time, and we're going to see which of them are okay to swap around and which of them are not okay to swap around. So for example, if I'm moving, this is your x-axis, if I'm moving right and then reflect in the x-axis, or I reflect in the x-axis then move right, you can see that I end up in the same spot. So moving left and right and then reflecting, the order can be changed. So you can reflect, then move left and right, or move left and right and reflect in the x-axis, because we're continuing with the x-axis. However, if we're moving up and down, let's say I'm translating up and then I'm reflecting in the x-axis, or I am swapping the order, reflecting first and then moving up, you can see that my graph has changed. So translating up and reflecting along the x-axis cannot be swapped in order. So again, reflecting in the x-axis, then moving up. See, I end up here, but if I translate first and then reflect after, I end up down here. So translating in the y direction and then reflecting in the x direction, you have to be very careful not to swap the order or your answer will be different. But translating left and right and then reflecting in the x-axis, it doesn't matter what the order is, your graph will end up in the same spot. So when we map or we describe this transformation, we have to be careful we end up in the same with the same graph. So it doesn't matter which way you go, but you have to end up with the same graph. So sometimes it matters the order, sometimes the order doesn't matter. So be very careful. Let's have a look at a few examples. Example 1. So we're going to recap this really quick, and we're going to look for the key things to be consistent with our answers. I'm doing this video in a rush, so don't mind me. I'm trying to maneuver this. Okay. So here we have the original graph and we're mapping it to this. So original and the mapped. Now the image or the map graph, I'm going to put a dash so I can recognize that that's my resulting image. And then what I do is I rearrange so all my y and translation numbers are together, and the thing next and the numbers next to x are together. So I'm moving the 1 over and the 5 down there so I can get this kind of thing happening. Now, because the left and the right now look similar, I can equate them. So y equals this chunk and the x equals this x dash minus 3. Now, once I've done that, I can rearrange and move the 5 over and the plus 1. And same thing with the x. So x equals x dash minus 3. So when I move the 3 over, I get plus 3. So the transformation, we can describe it as it has been moved to the right by 3 and it has been it has been dilated by 5 and then moved up by 1. So translate 3 units in the positive x direction, dilated 5 from the x, and that translated 1 unit in the positive y direction. Let's have a look at x squared. So this is a very similar example. So always put the dashes on the image and then write down, move everything to the left, or make sure the numbers next to x stay, and then move all the other numbers to the left side of the equation. So now we have y dash, bring the 4 over, I get, sorry, bring the 5 over, I get minus 5, dividing by minus 4. So now I let y equals this chunk and I rearrange until I get y dash by itself. And I get x equals x minus 3, and I rearrange until I get x dash by itself. So recap, you equate and then rearrange until the dash is by itself. And that's your mapping. So now we can describe. So here we have the x has been moved to the right by 3. It has been dilated by 4 from the x-axis. Remember, the number in front of y is from x. And then it has been reflected and moved 5 to up. But we could also take the minus 4 out and also describe it this way, which would be the x would be the same, so 3 to the positive x. But now we describe the 5 over 4 first. So 5 over 4 down. And then we describe the dilation and reflection. So always from the closest thing to out. It's kind of the opposite to when you're, you know, when you have an algebraic equation and you have to solve, you solve by moving the furthest thing. Well, when we're describing from the closest thing. Both things are correct, but I think this one is the one that we're most familiar with. So let's use that one more often, but I'll show you both ways. So here we have coming from something that is more elaborate to something simple. But remember, when it says something, something, something to the graph, then that is always the image. And you always put the dashes on the image. Once you put the dashes on the image, you have to make sure that the equation, which is messier with more numbers, is rearranged so that the x has a numbers next to it and y has numbers next to it, and then you can equate. So now this chunk is equal to the y dash and this chunk is equal to the x dash. Now we don't have to rearrange in this one because the y dash is already by itself and the x dash is already by itself. When you look in the previous example, when you equate this with the y and that x with the x dash, we had to do rearranging to obtain that line because the x dash was not by itself. Can you try not to shake the table, please? I'm almost done. Okay. So in this example, we didn't have to rearrange because the y dash and the x dash were already by itself. So now write down the mapping. So whatever is on the other side of the dash, that's your mapping. And then we can describe it. So moving 3 to the left, and then here we move 5, we dilate by a quarter in the x-axis, reflect in the x-axis. And if I write it like that, that means minus 5 over minus 4. That's positive 5 over 4, so 5 over 4 up. But I could also write it with a quarter outside. If I wrote a quarter outside, well, the x is still moving left to 3, but now I'm going from the inner. Remember, always the closest thing to y, so we're moving 5 to the right first, and then dilating a fourth in the x-axis and reflection in the x-axis. So I hope that clarifies it. Let's do one more example. So we're going to compare these two right next to each other. See how we're going from a messy one to a simple, and from simple to a messy one. Let's do these two examples right next to each other so we can see the difference. And then we're done after this. So here we're going from here to there. Remember, you always put the dash in your image. Now we move the 3 over here and the 25. Well, we're going to put it inside the bracket so that when we equate, whatever's inside the x squared is equal to x dash. So we have to put the 25 in the bracket. So now y plus 3 equals y dash, and that x over 5 equals x dash. Now the dashes are by itself, so our mapping is whatever's on the other side of the dash, so y plus 3 and the x over 5. So we can describe, so a fifth from y, so dilation of a fifth from y, and 3 up. here we have, so from here to there, we're going to put the dashes in the second one. I think I forgot to type dashes, but imagine there's dashes on this side. Now we rearrange, so bring the 3 over and then put that thing inside the bracket. Now we can equate, so y equals y dash plus 3 and x equals x over 5. Now after that we have to move our so y dash plus 3, I'm going to move the 3 over, so it becomes y dash equals y minus 3. And I'm going to move the 5 over, so I get 5x. In this line, I kind of skipped a step, sorry about that. So it was y equals y dash plus 3. Bring the 3 over, it's y dash equals y minus 3. And for the x is x equals x dash over 5. Bring the 5 over, x dash equals 5x. So the steps are always the same. Put a dash on your image. There should be dashes there. Then rearrange so you can equate. So the chunk of y things are one side, the chunk of x things on the other side. Then equate. And then make x dash and y dash by themselves. And whatever's on the other side, that's your mapping. And you describe that. So now let's describe this. So it's being dilated 5 from the y. And that 3 means it has moved down by 3. So you can see that these two are different, and you can see how we have worked them out. So always put the dash on your image, rearrange so you can equate, rearrange so the dash is by itself, and whatever's on the other side of the dash, that's your mapping, that's what you describe. Always describe from the closest to the outermost. In other words, the opposite to what you would do when you're evaluating equations. Now you can also read this by saying dilated 25 from the x-axis and translate it 3 units in the positive y direction. How can you say 25 from the x-axis? If you go back over here, if I left the 5, if I brought the 3 over here, so y plus 3, and then I brought the 25 over, so 25 y plus 3, so the 25 will be next to the y, then I would describe it as 20y from the x-axis. Okay, that's it for me today. I'll see you next time. Bye.